5 to 10 minutes, I will just brief you about this. So first we started with the motivation, why we need the photo detection. So we took some example from the astronomy, such as the telescopes. Then we look into the examples from satellite and solar cell, and also the OCT, optical coherence tomography, from the medical side. And then we went into some details of the CCDs and why we need fiber coupled photodetectors to detect the defect in the Wi-Fi. Then we came up with the historical backgrounds, that there was a wave picture or ray optics in the beginning. And with time, Maxwell started with his equations. And then finally, we have photoelectric effect. And we have these cathode ray tubes. And inside these vacuum tubes, photoelectric effect was done. And Einstein got the Nobel Prize for finding that light is not only a wave, but it is also a particle. So there is a duality, wave particle duality. And we established the formula E equals to h mu finally. And from this, we have now understand that there is a term called photon, and this shows that light is a particle. And then we started with the basic process of photo detection. So what is the photo detection? Photo detection basically start with first the absorption of the photons at this depletion region. Then these photons has to be generated electron hole pairs. So whatever photons are getting absorbed, they should generate electron hole pairs. And finally, these electron hole pairs should not get recombined. They should come out into the circuit and contribute into the current. So this was the basic process of photo detection. And then we see that, okay, anti-reflection coating is also required in order to remove the reflection and transmission coefficients. So then we classified the photodetectors in multiple domains. So basically the photoemissive, where there are no electron hole, only electron comes out, such as the photomultiplier tubes. And finally the photoconductive ones, where we only focus on the photodiode part, where I explain you the pin diode, and we did not look into the avalanche photodiode. We only explained you the pin diode. And then we finally classified some important parameters. So if you are a design engineer, which parameters you should take care about if you are going to build a photodetector. So such as the bandwidth, the response time, quantum efficiency, responsivity, NEP, all those things we established. And then I gave you some examples, how the formulas for each of these look like. So now let me go to one of this slide. Then next, what we establish is the responsivity, why it's increasing in terms of wavelength. And suddenly at higher wavelengths, we have a cutoff value. Because we go below the band gap, that's why the responsivity decreases. And here, since we have even the higher value of energy, but still we see lower responsivity. And the reason for this was very high absorption coefficient of the material. And the second is because these are very high energy photons, they create very high energy electrons, and these electrons dissipate non-radiatively in terms of heat, which is very fast in terms of femtosecond. So this was all about the responsivity. So let's begin today's lecture, which is about the noise, but let me first take up a problem. So suppose you have a pin diode, which is a silicon pin diode, and the power is given, which is 10 microwatt at a wavelength of 800 nanometer. Now some device parameters is given to you, such as the depletion width, the load resistance, the photocurrent. Then now let's try to solve some questions. So device parameters are given here already. Then the next is the material parameters, that what is the electron mobility, which is given here, and what is the diffusion coefficient, this is also mentioned. So if everything is present here, all the parameters is given to you, and if somebody asks the very first question that, okay, what is the photon flux? How many photons are coming per second and incidenting on the detector? So in order to solve this, what we need is, since we know this P is equals to N into h mu, or the energy of the photon, and N is the total number of photon coming per second. So power is given this 10 microwatt, and energy E is equals to hc by lambda. Hc we know, and the lambda is given here, so we can calculate the total number of photon which is incidenting on your detector. So the photon flux can be calculated if all those parameters is given to us. So I'm just trying to explain you some parameters of a photodiode and then what kind of question one can ask. So the next question is we need to calculate the responsivity of these detectors. So how do we calculate the responsivity? If you remember the formula, responsivity is how many photons are getting converted into current. So photocurrent divided by the total incident power. So since IPH is given to us, what is the photocurrent? This was already mentioned. So the total incident power is the current I divided by the P. And then finally, we have responsivity of roughly 0.45 for our detector. Similarly, I can also ask what is the external quantum efficiency for this. So we can also solve for the external quantum efficiency, right? We already know the formula that external quantum efficiency is responsivity multiplied by h into c divided by q lambda. Q is the charge, h is the Planck's constant, c is the velocity of light. And responsivity we calculated from the previous one. So this we know 0.45, lambda you know 800 nanometer, and charge you know, h you know, c you know. So if you put all this, the value comes out roughly 70%. So we have a detector which has external quantum efficiency close to 70%. Now, next question is what is the internal quantum efficiency? So what is the formula for internal quantum efficiency? This also, if you remember from the last lecture, we solved for this. So external quantum efficiency is related with the internal quantum efficiency in terms of 1 minus r minus t. R is the reflection coefficient, t is the transmission coefficient. In the question, it's already given that there is very less transmission, so we can neglect this. This will go to 0. And the reflectivity or the reflection coefficient is given as a value of 0.3. So we can calculate EQE, we know from the previous calculation, right? So we can also solve for this. And finally, we have a detector which has internal quantum efficiency roughly equal to 100%. So this internal quantum efficiency can go to 100%, but the external quantum efficiency practically will not go to 100%. So when I say internal quantum efficiency, meaning how many electrons are there as compared to the absorbed photon, not the incident photon. And this is also theoretically 100%, but in principle, some of the electron hole pair will automatically get recombined. They will not come out into the circuit and they will not contribute into the current, or maybe during the diffusion process, they will decay in terms of heat. We can also solve and ask what is the drift velocity and what is the drift time, because drift time in the end will contribute to the overall response of your detector, right? So we know that if there is a depletion region, there will be electric field. So these are just to revise you, just to brush up your knowledge. So if you divide voltage with the depletion width, so V divided by D is the E field, right? Voltage is given, the width is also given. So we can calculate the electric field. And if we know the electric field, what would be the drift velocity? The mobility of the electron multiplied by the electric field where this is present. So it is present inside the depletion region. So we multiply with the electric field which is present in the depletion region. And how much is this value, which is given here, 1 into 10 to the power 6. And the mobility, electron mobility was given due to the material parameters. So there it was also given, and we can calculate the drift velocity. So how much will be the drift? And as you know that total velocity is drift velocity plus diffusion velocity. And if we think about time constant, so drift time, then diffusion time plus the RC time. So if we try to calculate the drift time, which will be roughly in picoseconds. So if you solve this, because this is given, velocity you already know. So your detector has a drift time of picosecond, and also its bandwidth or the speed will be in picoseconds. So if a photon comes within a picosecond of time, you will see some sort of response. So that's all about this problem. So in this problem, you can even ask more questions. What is the diffusion current? What is the total current? What is the RC time constant? So there are multiple questions which can still be asked on base of this problem. But I will stop here. So I'll just given you some brief introduction from the previous lecture, and then I have also given you a problem, how you solve and go about all these things. So this will just brush up your basic knowledge. So since it is a lecture series on quantum, so it is very important to know about single photon detectors, because these detectors are basically the backbone when it comes towards the quantum optics. So if I ask you to calculate the energy of a single photon, which is coming from a laser of 630 nanometer, what would be the energy? So if you calculate E equals to hc by lambda, the roughly value will come out 3.14 into 10 to the power minus 19 joule. This will be the energy of a single photon. And if I ask you how much is the energy at room temperature due to thermal noise. So if you remember the formula, which is, we will also discuss about it in detail. So this is roughly 4 kb into T, where K is the Boltzmann constant and T is the temperature. So this value comes up roughly 10 to the power minus 20. So noise level is 10 to the power minus 20, signal level is 10 to the power 19. So it is very difficult to detect a single photon. It's not that easy. So there are some tricks what people do. So I'll show you a table. What we do is we create a pulse which is of a 1 nanosecond duration. And in that pulse, we have a single photon of this much energy, and we try to calculate the power. So power is simply E by T. If you do that, you will end up with some 3 into 10 to the power minus 10 power. So if you have this much power, within a single very short pulse of 1 nanosecond, if this pulse hit on an avalanche photodiode, so these avalanche photodiode are very highly sensitive. So per pulse, they can handle 10 to the power minus 19 or 18 joule of energy. So these kind of detectors are used in order to detect single photon. That is one kind of detector, which is avalanche photodiode. Now, I will tell you what is the cutting edge, what people are using right now, currently, what is being used in quantum. So what is currently being used is called superconducting nanowire single photon detector. Short form is SNSPD. And these detectors usually work at very low temperature, so roughly 1 to 4 Kelvin. So you have to cool down the system. And if you look at figure 1, so what they use is some sort of superconducting wires. So these are these superconducting wires. And as soon as one single photon hits on this, so this was a superconducting state, there will be lot of Cooper pairs. As soon as the photon hits on those Cooper pair, this Cooper pair will be gone. And then electrons will start to move and thermalization will happen in these directions. So first the Cooper pair was there when it was a superconducting state, and then suddenly phonon vibration starts, and this all happened in a very short time duration of femtoseconds, hundreds of femtoseconds. And now slowly resistivity goes up in this direction. So you can also see this in terms of signal and time domain. So on the x-axis we have time, on the y-axis we have signal. When it was in the superconducting state 1 and 2, the signal was quite low, and consider signal is a voltage. So it was very low. As soon as you hit with a photon, thermalization happens, a lot of electrons are there, and then they started to move, they collide with each other, a lot of phonons are getting created. Once that happens, the resistivity increases, hence the voltage increases. At stage 4, what you do is you ground this electrons, and then once you ground, all the electrons will go to the ground, and then again you come back to the superconducting state. So after 4, you go back to the 5 and you come back to superconducting state. And this is what is shown with the simulation as well. So these kind of detectors, they work at very low temperature and they work from UV to mid-infrared. Whatever photon comes up, they are able to do the detection. And these kind of detectors are very sensitive and very expensive. So I have shown you the mechanism, a basic idea how the single photon superconducting nanowire detectors work. Now, when I showed you here at slide 1, so they use superconducting nanowires. This is how the structure looks like. So that's the some sort of wires arranged in some sort of zigzag grating pattern, and that's a superconducting nanowire detector. The distance of one of these, the width is 100 nanometer, and the total length is 16 micron, and they are made up of a material called niobium nitride. So there is a company called IDQ. They create these kind of detectors, and the cost of one of these detectors is roughly 1.2 CR, 1.2 crore rupees for one single detector. And they work on the superconductivity based principle. So you have to maintain very low temperatures. Now there are some emerging trends in these photodiodes. So currently people are moving towards 2D materials. They want to use 2D materials to make these detectors. Also, you have seen some flexible mobile phones or flexible displays where quantum dots are being used to create photodetectors. The next is integrated photonics, where people want to make things on a chip. So in 2025, there was a famous paper published in Science where they have used 2D materials, these kind of materials, to create single photon detectors. The benefit is that you need not to go to very small temperatures, 1 or 4 Kelvin. You can do things at room temperature. The second paper published in Nature Communication in 2021. So on a chip, they have created a superconducting nanowire based detector, single photon detector, which is created on this chip. So there is a lot of effort which is being put on to create these kind of single photon detectors. And I think in some other lectures, you will listen more about single photon detectors as well. But this was the basic idea, what is currently happening in the field in terms of detectors. So now let me give you some real life experiments also. So during my PhD and postdoc times, we also tried to create some photodetectors. So I will explain you how a Schottky photodetector is created. So the idea is we have a target substrate. This is TiO2, and we would like to make nanoparticle chains on top in a grating fashion. And once we have a TiO2 and metal nanoparticle, there will be a Schottky junction in between. So this will be a Schottky junction. How we do this? So we first start with the process of fabrication of gratings. So we take two beams, we do interference lithography, and we create patterns of 1D lines. Then we take a solution called PDMS. It's a very flexible material we put on top, and then we finally cure this material and then peel off. So this was the master template, and then we create a replica of it. And this is called the PDMS template. Finally, we take the target substrate and we put the drop of these nanoparticles which we want to place on top. And finally, we press this droplet with this replica of PDMS. And in the end, we have our nanoparticle chains available on a target substrate in grating fashion, right? So here what I have is a glass, then I have a TiO2 target substrate, meaning I have a layer of TiO2, which is a semiconductor, and metal gold nanoparticles. So the sample will create, in one side you have gold, which is a metal. Another side, from physics point of view, you have TiO2, which has valence band and conduction band. If you shine light on this sample, lot of hot electrons will go up because they are very high in energy, and then they will move towards the conduction band, or they can also tunnel through. So there can be a tunneling current, or there can be a simply movement of electron towards the conduction band because of the band bending. So if let's see how the sample looks like. So this is the sample, this is glass sample, and you see this pink color is due to because I have deposited a layer of TiO2 on this glass. Now this is the area where I have done the gold nanoparticle chains, and finally I deposited some metal electrodes on top. So these are the metal electrodes which I deposited on top. So this same sketch look here, this is from the side view. So we have glass, we have TiO2, we have nanoparticle chains, and we deposited two electrodes, and we apply a certain voltage to these two electrodes. If you look in the optical microscope, this is how it looks like. So these are the electrodes, 1, 2, 3, 4, 5, and in these two electrodes I have applied a voltage of 1 volt. So there is a bias voltage, And in this area, you have these nanoparticle chains arranged sitting on TiO2. And this much length is called the channel length. Because I'm using this and this electrode, I have given a voltage, and this channel length is roughly 350 micrometer. Now I will shine light on this sample. As I explained you, what happens is that as soon as I shine the light, lot of hot electrons will get created and these electrons will move towards the TiO2. Because of that, the conductivity of TiO2 will increase and the resistivity go down. So what I want to see is that as soon as I shine light on it, how does the system responds to the light? So if when I shine the light, if a lot of electrons getting generated, so there should also be the current getting generated. And these electrons will move in one particular direction because I have applied a voltage. So there is definitely a voltage, and because of that voltage, they will move in one particular direction. So let's see how this looks like in lab. So that is the whole setup where we will do the current measurement. That is the LED which is shining from the top. So green color is due to the LED. And these are the tips which you attach to your gold uh, electrodes. So these two gold electrodes which you have deposited, you attach these two tips and try to measure the current values. So if you look at it, this is how it looks like. So for 565 nanometer, for this particular wavelength, as soon as you shine this wavelength, there will be current going up, and then you shine the wavelength for 20 seconds and then it comes down. You shine again, it goes up and then comes down. So you see that for this particular wavelength, you have a good response. As soon as you increase the wavelength, because of the energy reasons, the system does not oscillate, and then you do not see any current formation for, let's say, 780 nanometer. So finally, what you have is a system which is responding to a particular wavelength. As soon as you shine the wavelength, it gives you some photocurrent, and this current is in nanoamperes. And what we are doing is we are giving some, for some time we switch on the laser or the LED and then we switch it off. 20 seconds again switch off and then switch on for 20 seconds, then switch off for 20 seconds. So this is how it is moving. Now, if it is a detector, we can also create those responsivity, NEP, quantum efficiency things for this. So if you remember the formula, so this is photon to photon conversion efficiency. So this formula is equal to responsivity actually. So if you remember, the same things are there. So it's the same formula. What you need in order to calculate the responsivity is the wavelength, which you know that which was 565, which you incident. J means the current density. So you have your electrodes, and if you shine the laser or the LED here, they'll calculate this total area and the current value you have, which is let's say 3.5 nanoampere or 4 nanoampere, you divide it by this particular area. So you have your J value. And if you want the P, which is the power of the source, so once you purchase this LED, the power of this LED is given, and you can also use a power meter to calculate the power of the LED. So this, all the values what you want is there for you. So finally, we can calculate the IPCE values. And this is how it looks like. So for 565 nanometer, we have the responsivity data. Looks like we have roughly 20 value nanoampere per watt for the 565 nanometer, and for 590 the responsivity value go down maybe 1 or 2. So I just wanted to give you a brief overview that okay, we can also make these kind of devices in lab, and we can also check back all the characteristic values for such devices. So now let's move to the topic of noise. So usually what we have heard a term is signal to noise ratio, meaning signal is something which is wanted in nature and noise is something which is unwanted. So usually a detector is good if the noise levels are lower, right? So let me draw a noise signal. So this is the y-axis, this is x-axis, and you can draw a random signal like this, and this we will call it as a noise signal. Now we usually say that noise is random in nature, but it all depends on the time scale. So if you talk, so this is the time axis. And if you talk about smaller time scale, definitely noise is random. But if you talk about a bigger time scale, noise is not random, it shows some characteristic. So if you have a signal which is noise, if you want to know about this signal, there are two ways to know about this signal. Suppose you want to know how much is noise is there and how much is the variance in the noise, how much is the fluctuation. So there are two ways to do it, and it will go deeper into the mathematics. So one way is you take the signal and try to solve it through time domain. The second option is you take the signal and try to go about it using frequency domain. So if you go with time domain, you take the signal and try to plot the probability distribution function. And if you take the frequency domain, you try to plot the power spectral density. So just to give you an example, suppose you have a lens, that is the axis, and you have a point here, and you want to make an image of this point. So one goes like this and like this. And then finally, let's say we have this point. So image of a point will not be a point, it will actually be a airy disk. So there will be some power spectral density distribution. And this distribution can be found out. So it will not be a point, there will be some spread of this point in X or Y axis. So similarly, noise is there. Noise is a random signal, but it carries some sort of statistics fingerprint. So I will in this talk always talk about probability distribution function, and we will take the time domain route and we will try to solve through time domain. So just a brief recap, what is noise? Noise is some signal. We want to know about this signal. There are two ways you can do it, either in time domain or frequency domain, and we will talk about in terms of time domain, which is probability distribution function. So let's say we have a signal in terms of voltage versus time. So if you are moving in terms of times, the voltage is fluctuating. So there are changes in the voltage. Now, if you use the time domain, what you can do is you can try to plot the changes in the voltage. So maybe if this is the mean value and you go at the very first time instance, you say, okay, the noise is this much, I will plot it here. So voltage is maybe 2 volt. And then you keep doing it for the whole complete signal. So you try to plot the probability distribution function. Now this probability distribution function has some important features, so I will tell you. So if you look at it, this is somehow looks like this. So this is what has been plotted here. So it looks like this. What is the mean value? Mean is given by a term called mu. So the mean value will be at the center, which will be mu, meaning there are a lot of fluctuation, but what is the mean value of this fluctuation? This will be this value. Now, the another term which is important is the standard deviation. So how much is the standard deviation, which is called with the term sigma, and the third is the variance, which is sigma square. So there are three important terms: mean, standard deviation, and variance. Now if there is a graph, then suppose the mean value is this, it is possible that only within this envelope fluctuations are there. There is a very less probability that there are fluctuation here as well. So there is at some particular time always fluctuation might be from this point to this point. There is no way that there are fluctuations here. There is no fluctuations here. So what you try to do is if you go 4 sigma away from your mean in this direction and 4 sigma away from your mean in this direction, you have roughly 99.9% of the things or the fluctuations are covered. So if you go just 1 sigma away, roughly 68% of probability is covered that everything lies within this range, which is 1 sigma in positive direction, 1 sigma in negative. And if you keep increasing, so if you go 4 sigma in this way and 4 sigma on the other direction, you have roughly 99.99% of fluctuation covered. So always think that noise can be represented in terms of some statistical variations. So this statistical variation is called a Gaussian distribution. And in this Gaussian distribution, we can define terms, which is the mean value, standard deviation, and variance. And this is how it is plotted. So with time, whatever fluctuations are there in the voltage, I can plot it. Once I do the plotting, this is how it looks like. So What can be other type of distribution? So there can also be a Poissonian type of distribution, and there is a Gaussian type of distribution, which I just explained you. So now let me give you some examples that how this noise is not random. So in a smaller time scales, it looks random, and on a bigger time scale, it is not random. So let's say we try to calculate how many people are entering into a mall every 5 minutes. We do this exercise. So people come in every 5 minutes. I write down how many people came in within that 5 minutes. So let's say first 5 minutes, 10 person come, then 14, then 9, 12. So I wrote down the values. Now after 13, if I ask you, okay, tell me how many person will come in the next 5 minutes, you have no clue that how many people will come in the next 5 minutes. Maybe it can be 15, it can be 5, it can be 23, it can be anything in the next 5 minutes. You don't know the value. So this looks random in a smaller time scale because you cannot predict how many people are going to come in the next 5 minutes. But after you do this exercise the whole day, and then if I ask you, you take the average value and you see that, okay, in the morning hours, the number of people were low. And then in the evening hours, after the office hours, the number of people are high. So when I was asking after 5 minutes, you were not able to tell a number. But once you look at it for the whole day, complete story, then you can give me some sort of analogy that, okay, maybe from 2 to 5, there will be less people present if I ask for the predictions for the next day. So this is one example that I'm trying to connect with the noise, that if there is a signal which is very random in terms of smaller time scale, it is possible that on a bigger time scale, there is some sort of pattern or some characteristic which we can take advantage of. So now it is not random anymore, right? There is a pattern that at some particular time, there are high number of people and low number of people. Let me take another example, which is the rainfall example. So suppose rain is happening in the morning 6 o'clock, and I ask you at 6:01, or after just 1 second, I ask you that, okay, tell me where will be the next drop will fall down on the ground. You don't know where will be the next drop fall down. Maybe it will fall somewhere here or there, but after 1 week or 1 year, you can do the prediction that, okay, in the month of August to September, there is high rain. And in the month of Jan to Feb, there is very less number of days where the rain is happening. So just think in this domain. This is called in mathematics, people know it central problem. So this is very common in terms of statistics. So what is the take home message is that noise is random in a shorter time scale, but if we go on a bigger time scale, it is no more random. So then noise has some sort of distribution. There are two major distribution we talked about. One is Poissonian and the second one is Gaussian distribution. So I will tell you explain you what is Poissonian distribution. So this is how the formula looks like for Poissonian distribution. And I told you there is a value mu, which is the mean, and there is a value sigma, which is standard deviation, and sigma square is variance. So if variance is equals to the mean, then you call these kind of distribution as Poissonian distribution. So this is the typical characteristic of a Poissonian distribution. So let me take an example. Suppose we have a laser, and in a particular length or a segment of line, there are 4 photons available. And some other instant of time, there are 5 photons available. At time t3, maybe there are 3 photons available. So you don't know how many photons are available. This is happening randomly. Now you can write down the formula for this, which is what is the probability of finding n number of photons. So probability of finding 0 photon, or probability of finding 1, or probability of finding 2 photons, which is dependent on this formula because it follows Poissonian statistics. And n is 0, 1, 2, 3. So for example, let's say the mean value is 1, n equals to 1. And let me try to find the probability of 0 photons. So n is 0, n bar is 1. So if you put in this equation, n is 0, 0 factorial is 1. and e to the power minus 1 because n bar is 1. So this has become e to the power minus 1. And since n here is 0, so sorry, this is n bar is 1, 1 to the power 0 is also 1. So this will become 1 by e, right? So probability of finding 0 photon is 1 by e. Similarly, you can do this exercise and see probability of finding 0 photon was 1 by e and 1 photon is again 1 by e. You can put all these values here, and for this n will be 1 and n bar is again 1, and if you put n equals to 1 n bar 1, you will end up with 1 by e. So the probability of finding 1 photon is also 1 by e. So here we see probability of finding 0 photon is roughly 1 by e, probability of finding 1 photon 1 by e, and if we move next, probability of finding 2 photon suddenly drops down. And then if I say probability of finding 10 photon, which is 0. So how is the distribution? Distribution looks something like this. There is no more a Gaussian distribution, or it is not symmetric about y-axis. These kind of distribution where you have the mean equals to the variance, this is called the Poissonian distribution, and they follow this kind of equation. So in this, the fluctuation, which is sigma, will be equal to mean value under root. So this equation will hold in case of Poissonian distribution, right? Now, depending on the type of distribution, you can also classify the light. So if there is a light source which follow this Poissonian distribution, we call it a coherent light source or lasers. So lasers come under these kind of light source category. Then the light sources which follow the distribution where your fluctuation is greater than the under root of mean value, these are super Poissonian. So meaning this kind of distribution. This is sort of Gaussian distribution or Bose-Einstein distribution. So usually the thermal light sources or incoherent light sources, they follow this kind of distribution. And finally, the sub-Poissonian distribution where fluctuations are very less than the under root of mean value. There is no classical light source which follow this kind of distribution or sub-Poissonian, meaning this one, this distribution. So there is no classical light source which follows. There's usually all the quantum light source, they follow this kind of distribution. So what I'm trying to tell you is that noise follows some sort of different distribution, Poissonian, Gaussian, sub-Poissonian, super Poissonian, and there are also light sources which are defined or categorized in terms of distribution, and noises is also categorized in terms of distribution. So let's talk about the thermal noise. People also call the same noise as Johnson noise. And let's see what is the reason. Why do we have this noise? So the very main reason is the temperature to have this noise. And because of the temperature, the carriers started to move. And once they started to move, they have heat, they collide with each other. Once they collide, they lose their energy in terms of phonon, and they have this thermal motion. So suppose you have a resistor with resistivity of 50 ohm, 100 ohm, there will be thermal noise. If you have detector materials, silicon, indium gallium arsenide, you will definitely be having thermal noise. So what is the formula for this thermal noise? So the formula for thermal noise is 4 kBT R into delta F, where delta F is the bandwidth and R is the resistivity and T is the temperature, K is the Boltzmann constant. So suppose we have a circuit where we have 1 kilo ohm of resistor and we apply a voltage of 1 volt and we want to see how much is the current. So typically the current will be like this, right? This is what we expect, but in reality the current will not be a straight line, there will be fluctuation, and these kind of fluctuation comes from thermal noise. So you see that it's up down up down up down, so there's not a constant line. Now remember that we called something like dark current. So dark current meaning when there is no photon incidenting, there is still current, and the thermal noise is the reason. So if you increase the temperature, there will be more thermal noise and there will be more dark current. But the dark current itself is a short noise. It's not a thermal noise. The reason for having dark current is thermal noise. And thermal noise is a white noise. So white noise is something which is not dependent on the frequency. So if you increase the frequency or you decrease the frequency, the thermal noise is not going to change because it is heavily dependent on temperature, not on the frequency. And this thermal noise shows a Gaussian distribution. So if you try to plot the power spectral density or the probability distribution function, this will show a Gaussian distribution. Now this is how it looks like. So if you have a frequency in X domain and the power in the Y, so 4 kTr, uh, this will be your uh, noise, thermal noise signal. So that is all about the thermal noise. Now we move back to short noise. So what is short noise? So short noise is generated because of the randomness in your light source. So as I told you, the light source also are differentiated in terms of their photon statistics. So coherent light source are anti-bunched and the incoherent light sources are there, and maybe quantum light sources are there. So in quantum you will see lot of short noise, and the systems which are below short noise, if you prove that, then only you could say that you have a quantum system. But why this short noise happens? This short noise happens because the photons arrive at random time. So let's go back to our very basic picture. So we have this PN diode, which is in reverse bias, and we have electron hole pair, right? And a photon is incidenting. When I say photon is incidenting, one photon is coming, or maybe 10 photons is coming. Now, I don't know when the next 10 photons are going to come. Exactly at what time, I cannot announce it. So, what is the problem? So, these photons are coming from some light source, right? They must be coming from somewhere, from some sodium lamp, from sunlight, or from a laser. Let's suppose that they are coming from a laser. So what is a laser? Laser is again a semiconductor gain medium. So if they are coming from a semiconductor, there will be conduction band, there will be valence band. And you will first pump the laser. So the electron will go at the conduction band and then it will decay and then a photon will come out, right? So it will come back and a photon will come out. So exactly at what time this electron is going to come down, that I don't know. That's a spontaneous decay process. So every band has its own lifetime. So this conduction band, electron can sit there maybe for 10 nanosecond or 10 picosecond. There is a lifetime. But within that picosecond, will it come down at 8 picosecond or 6 picosecond or 4 picosecond? That I don't know. And this inherent randomness created the short noise, that the first photon maybe comes at 1 second, the next one comes at 1 plus 8 picosecond, the third one comes at 1 plus 8 plus 7 picosecond or something. So there is not constant interval, there is a random interval between the photons coming. And this is again, short noise is also a white noise, so it is not frequency dependent, right? So if you try to plot the statistics, they will follow a Poissonian statistics. So short noise shows a Poissonian statistics, and this is the total power of a short noise looks like, right? So where Q is the charge of the electron and I is the average current. So if suppose a dark current is flowing, and first you have to take the mean value of this dark current. So I said you this mu is the mean, sigma is the standard deviation. So you have to consider the mean value of the current. That value you have to put here, and delta F is the bandwidth. And then you can calculate how much is the total short noise power. So again, to explain you a little bit in more detail. So let's say we have this junction, which is this PN junction, and you hit with the photon, right? And it's a coherent light source. So meaning you have a bunch light source, meaning some 1, 2, 3 photon packet is there. Then there is a gap. Then again there is some photons. Then maybe there are 4 photons together, right? So this is these type. If there is this kind of distribution in photons, this is called a bunch light source. Meaning there is a different time in between these two, and there is a different time in between these two packets. So if a photon has these kind of statistics, and if this photons is hitting on this depletion region, right? Let's say this is the stream of photon coming. So this photon comes and hit, you have photocurrent. This photon comes and hit, you have photocurrent. Maybe this photon is gone. Maybe the material did not absorb it, so there is no photocurrent. and this comes, there is a photoelectron. And out of these photoelectrons, you will see current pulses are getting generated. So whatever is the distribution which is present here, roughly more or less same distribution you will find in also your current pulses. So if it is a bunch light which is following a Poissonian statistics, the same sort of statistics and variation you will also see in your current pulses. So that is the main crux of the short noise. And it is a white noise which follows a Poissonian statistics. If you look at the thermal noise, this is also a white noise, is not dependent on frequency, and that follows a Gaussian distribution. Now comes is the flicker noise. So flicker noise is there. Suppose if you have, so I showed you, we take a glass slide and we deposit TiO2 materials on top. Suppose if you have a material where the conduction band is there, and this material is imperfect, so you did not heat the material and the crystalline phase is not there, and there is a lot of trap states are present. Suppose if your charge is stuck in these trap states and then suddenly it drops back, so there will be some photon arrival or some current contribution. If this charge is trapped in the state and it's not giving any value to the current, so the current will be slowly suddenly gets lower. As soon as it goes down, the current is higher. So because of that fluctuation in the availability of the trap state, so trap state is getting suddenly occupied and then deoccupied. So this fluctuation in the occupancy create kind of flicker noise, right? So suppose these are the trap state and suddenly these two trap states are filled. And after, let's say, 1 second, this trap state gets empty and then this trap state and these two are filled. And then after some time, this get filled, and then after some time, only this is filled. And so there is continuously fluctuation is happening. And because of this fluctuation, you have changes in your current because you have changes in the trap state. And trap meaning charge gets stuck here, and suddenly when the charge comes out of the trap, it contributes into the current value, and then suddenly your current will spike. As soon as the charge gets stuck here, there will be a dip in your current. So you can get a dip once the charge gets stuck. Once it gets free, you can get suddenly a enhancement in your current value. So if it is happening in a single trap, then usually we call it a telegraph noise. But if it is a combination of a lot of occupancies, then all combined together, we call it a flicker noise. And remember that flicker noise is frequency dependent. So every trap state has its time constant that the charge can stay there for maybe nanosecond or picosecond, and after that the charge will go back and it will contribute to the current. So every trap state has its time constant, and usually if you go at higher frequencies, whatever changes are happening there doesn't matter or does not contribute into the noise because you are working at very higher frequencies. So you're working at very smaller time scales, and then it doesn't really matter that what is the because these time scales are a little bit larger as compared to. So if you go to gigahertz frequencies and all, there is very less amount of flicker noise or telegraph noise. So this kind of noise is frequency dependent. And usually it is very dominant at, let's say, kilohertz to megahertz range. And you know that why this is there. This is because of the you create a lot of defect or traps in your structure. So if you want to reduce this noise, what you have to do is you have to create a sample which is very neat and very super crystalline. So with a function of time, suppose you have a TiO2 deposited, you heat it up to 300, then 500 degrees, and then this TiO2 will be converted in Anatase phase. And then you see how much current is there. If there is a lot of trap or occupancy, you try to deposit a better TiO2 material. So it's all dependent on your material, how this looks like. So now how this flicker noise is dependent. So this flicker noise is dependent on 1 by F. There is a constant which is K. And again, there is this current value I, which is the mean value average of your current. And these constant A and B. So B is usually 1 and A is usually close to 2. So it depends on the I square value. So if current also increases, then this value at lower frequencies is also increasing and your noise amplitude goes up. So usually what you do is you try to make a very clean surface. And this follows a non-Gaussian distribution. So this does not follow any Poissonian distribution, does not follow any Gaussian distribution, and it follows a non-Gaussian distribution. And typically you also call it a random telegraph noise. And as I said, telegraph noise is there for the one single trap. And once there is a bunch of trap and the effect is from multiple of these, then you call it a flicker noise. So if you try to plot the voltage of the flicker noise with terms of frequency, this is how it looks like. So as soon as the frequency increases, it goes down. So at the higher frequencies, and this is some people call it crossover value. And after the crossover value, the short noise is dominant, and before that, flicker noise is dominant. And once you cross a particular frequency, you will mostly see short noise. You will not see flicker noise. So that is mostly all about noises. Now let me explain you why we cool our detectors. So usually if you have worked in the lab, what you see is that we try to cool the detectors. So in terms of temperature, what we can humanly achieve is 0 Kelvin. So that is the absolute zero temperature which we can achieve. And if you use a material like liquid nitrogen, you can reach up to minus 200 degrees or 77 Kelvin. And just to give you a reference, that room temperature is 25 degrees, so roughly 300 Kelvin. And what you use is liquid helium, which can take you to even lower temperatures, which is roughly where superconductivity happens, so 3 Kelvin. And superconductivity based quantum computers, they use dilution refrigerators. And these dilution refrigerators can reach a temperature up to close to 0 Kelvin. So the thing is that, let's say at room temperature, how much noise is there? So we can use the formula 4 kb into T at a 50 ohm load, and you can find out that there is roughly a 0.57 microampere of current at room temperature. So that much is noise is there. As soon as you cool down with the liquid nitrogen and temperature goes down, you will see that there is a drastic change in the current and you go from 0.5 to 0.2. So roughly you reduce the noise by half. And that is the reason we try to cool the detectors, because, and other way around, if you see, it is always useful to make a detector at room temperature. So finally, what I have created is a table, and here you could see a different type of noise type and which kind of statistics behavior this noise shows, and what is the relation in that statistics in mean, variance, and standard deviation, and what is the typical origin of different noises. So in today's lecture, this is all what I wanted to cover. And thank you all for listening, and I'm open to questions. Please feel free to ask or write in the chat.
Thank you, Dr. Vaibhav. And participants, if there is any questions, please feel free to write in the chat box so that the speaker can see and respond accordingly.
Yeah, please write your questions in the chat.
And if you want to ask directly, please raise your hand so that I can unmute you so you can ask the question directly with the speaker.
Yes, so this quantum computer in IISc, this is based on photonics, and basically not on a chip, but this is on an optical table. And this is from Professor Chandrasekhar's group, and this is a 6-qubit quantum computer, which is being demonstrated in IISc Bengaluru. So actually the good thing about these kind of quantum computing systems is that you do not need very low temperatures like dilution refrigerators. So each dilution refrigerator might cost 10 to 11 crore rupees. And using optics is makes cheaper, but then there are other problems in using quantum computer, that the scaling becomes a problem, that you cannot scale it at a level what you want. So going from 6 qubit to 10 qubit might be very difficult, and then the amount of optical components you require will scale very much.
So, and Dr. Vaibhav, how did they apply input?
So I did not get it. How did they apply input air? Is it like?
It is like regular keyboard or files?
No, no. So, for example, what you know is there is a Qiskit tool available. So there is a quantum computer at the back, which is created by IBM. And what you can do is you can run your quantum algorithm. So you have to write some sort of algorithms using different sort of gates. And then you give this algorithm to this computer, and then this computer try to solve it. So you give it in terms of, yes, you use as a keyboard, you write your code, and then this code will be run. And then, so quantum computer does not work for each and everything. There are certain problems for which this computer will be useful. So what you are saying in terms of file, that might be the quantum algorithm. So you have to create some algorithms, and then this you can apply to this computer. The direct interaction is not possible. So as soon as you do the direct interaction, so there is a problem of collapse in the quantum. So once the quantum system comes in contact with the regular things, there will be a lot of coherence problem. So this is not possible.
Okay, so thank you, Dr. Vaibhav, for your session.
Thank
So
you,
there
sir.
is
Thanks a
no
lot.
question. So I think we should stop here for the first talk. Our second speaker has already joined. So
Yes.
thank you, Vaibhav, for your talk. And now I am introducing our speaker for this session is Professor Rajan Jha from Department of Physics, IIT Bhubaneswar. His research interest in the area of coupling photonic nanostructures to nanowaveguides and resonators, semi-classical and quantum interferometer, instrumentation for industrial application, structured light, flexible and variable photonics, plasmonics, and today he is going to give a talk on the sensing technology. So, sir, I welcome you for this faculty diploma program on quantum sensing.
Okay, so good afternoon, everyone. I hope I am audible.
Yes, sir, perfect.
Okay. And also, are my slide visible to you? No, not
Yes,
yet.
not in the presentation mode.
Okay. Is it fine now?
Yes, perfect, perfect.
Okay. So, good afternoon. So, I am Rajan Jha, and I would like to thank Prof. Awasthi for this opportunity to give this opportunity where, I will be presenting some of the work that is going in my group, but this is more of a general talk. So this is not much specific either to some of, I mean, we use some of these technique in our work here at IIT Bhubaneswar. So as you can see, the title of today's talk is, sensing technologies. So this can be both classical as well as quantum. Now, as we go ahead with the talk, we'll realize that what do I mean by these, classical and quantum? Uh, one can identify classical and quantum. In the previous talk, you heard about some quantum computer which are being developed in the country now. And classical is something we say, okay, this is the classical style of Sachin Tendulkar batting. Like, so you correlate these to more things which are more visual in nature. So, and quantum is something which we do not perceive in our day-to-day life. So as we go ahead, this thing will become much more clear. But before, I proceed further, I would just like to invite all of you to visit our campus in Bhubaneswar. This is the main administrative building what we have. And, whatever we do in our group are credit to all these people who are standing here. These are all my research scholar postdocs. And being experimental lab, these research are not possible unless until it is funded by the funding agencies, starting from DRDO, ISRO, SERP, MHRD, BRNS, National Quantum Mission, Optica. So I must acknowledge all these people who have been either behind the scene working as a workforce, or the funding agency who has been very generous in giving us, and some of the fellowship by the government of India. I hope my slides are moving. Is it moving?
Yes, sir.
Okay, fine,
Move.
good. So this is the outline of my talk. We'll be talking about something about sensing and why it is so important in the present context. And then what are the two paradigms of sensing, like whether it is classical or quantum, and what are its working principle and application. And are there any advantages of quantum systems or quantum sensors over classical systems, followed by some discussion. Let's just talk about what is sensing as such. So if you see a human body, we have 5 sense organs, right? All of us know that we have 5 sense organs, and these are the organs through which we perceive different type of feeling or sensation as a human. So if you have to define some sensing, it is some sort of a process through which we detect or measure any of these parameters. It can be physical parameter, it can be chemical parameter, or it can be biological parameters. So these, whatever the signals that you obtain, in order to measure those signals, you use one of these techniques. It can be electrical technique, so you measure in terms of current and voltage, or it can be optical techniques where you try to measure them in one of a parameter which is related to optics or light. The different attributes associated with lights, for example, is intensity, wavelength, phase, polarization. So these are some attributes which are associated with light, like what are current and voltage attributed to electrical. And similarly, some mechanical systems are also there. So where you try to monitor, again, I mean, it is more of a systems where you try to correlate in terms of different Young modulus of the system, or a stress and a strain analysis of a system. So that depends upon which parameter you are talking about. So mechanical systems largely get categorized or measured using physical type of a process. So what this sensors does, so it just convert these signals into one of a parameter which we can measure in our lab. So you can see these 3 diagrams, right? As you can make out that in news, you will many times see, or you will hear in the news that a bridge get collapsed, or some sort of a accident has happened due to some sort of a crack in the bridge. So one need to monitor the health of this bridge. So that largely fall under physical systems, which can also be categorized to mechanical, analysis of using some mechanical signals need to be detected. Chemical sensing is something which a lot of us does in the lab, where you do a lot of experiments and you try to monitor the different type of organic uh, substances or inorganic substances, depending upon what you are interested in. This diagram of a biological sensing is must be known to all of you. This is a scary diagram during 2019-20, because this shows the spikes of some of the coronavirus which infected the whole world. So these are some biological sensing which one need to do. So all these sensing, you have to develop some sensors, and these sensors must able to identify these particular parameters or signal from one of these, in either as electrical output or as an optical output or as a mechanical output. So with this is a brief introduction about sensing, it is very important that, as a human being has evolved in such a way, from depending upon the requirements, they have developed the technology, and these technology get largely governed by the market price, or the market of those technology get largely governed. uh, the research in those technology largely get governed by the market. And if you see, this is a diagram which shows you how does the global sensors market look like from, let's say, for from 2022 to 2032. You see, it is some sort of exponential rise. So the major and these numbers, what you are seeing is close to around 230 billion US dollar. So this by 2032, this is what is expected. Please note that out of these are the sensors which are utilized largely for many applications, and one of the most important sensors are pressure sensor. So if you see this diagram carefully, you will realize that from beginning, the pressure sensor shares a majority of the portion of the global market. And then you have, of course, pressure and temperature. Of late, with the advent of, large data transfer rate, uh, using different means of communication, image sensor has also become very important. You try to do the image analysis and try to identify whether how many vehicles are crossing the road, or whether some accident has happened on the road, or for example, in biological applications, if you have to image some biological cells, live cell or dead cells, which are harmful for human. So people use a lot of image sensor. Please note, when we are talking about the image, we are talking about the signals in terms of optical signals. Pressure sensor can be in electrical as well as optical as well as mechanical. And therefore, since you can monitor by taking the beauty of any one of these signals, therefore you also see that it has a lot of market. So depending upon customization, how the sensor can be customized, one can utilize either electrical signal as output, optical signal as output, or mechanical signal as output. And then there are, of course, gas sensors. Professor Avasthi extensively works on the gaseous sensors, so he can share with you more about that. And then the other fall is all other type of sensors, whether it is sensors that we are talking about for industrial application is vortex flow meter, accelerometer, or for example, you are talking about any type of biochemical reactions or biological sensors. So driven by this market, there's a lot of, it is expected that this area will further grow with advent that now you have a very strong AI moving around. Then integration of all these data driven systems, which can be addressed by AI, but sensors cannot be, AI can be utilized for development of smart sensors, but the development of sensors is important for monitoring the physical, chemical, and biological parameters. So why the sensors are important? Now this give you a quick view where human being is getting, touched every now and then through sensors. So one thing is very important is environmental monitoring. We know that there are a lot of gases there are environment which are not good for health, and the emission of those gases need to be identified. So one can do those using one can do those using development of sensors. When we go to airport, we see that there are many sensors which are there. As soon as you enter the gate, there is some beep sound that happens, and you go through some scanning process and stuff. So safety and security has a lot of sensors inbuilt in it. Uh, with the advent of industrial 4.0, or for that matter going towards 5.0, in future you can always expect that to automate the industrial products, you require a lot of sensors of how these robots arm will move, how much it can take the load, what is the stress that it is experiencing, whether it is working fine, whether it is damaged, or what is the health of these robots, so on and so forth. Needless to mention, all of us use mobile phone systems, and the way communication systems has evolved, you require a lot of sensors there also, while while you are transmitting the data or you are collecting the data. Then there are smart cities being built up, and it is expected that in near future you'll have some for transportation and real time usage. With the advent of we are in 5G. So if we go towards 6G and 7G, it is expected that everything will going to be smart, and every of these vehicles along with the flight will have the internet facility. Vehicles of course still require one can use a Wi-Fi within the vehicles, but then everything being linked to some common port where you can utilize these vehicles for different type of navigations application, as well as for using them as a smart vehicle. uh, Healthcare is one area. After post-COVID, people have become very cautious about it, and there are a lot of research which are going in healthcare diagnostics, where different type of sensors, which we also work in our lab, we call this as a photonic wearables, which can be utilized for human physiological monitoring. This is something which is future, and there are a lot of research going across the globe in the area of quantum applications. So I have broadly say as quantum applications because using these quantum sensors and quantum metrological systems, one can precisely determine some of the parameter which otherwise is not possible with the classical sensors, which we'll be discussing about. So once you know the importance of these sensors, another thing what we would like to know that how to know that which sensors are good, which are not good sensors. So there are some performance matrices of the sensors which is acceptable across the globe. I mean, these are the parameter on which any sensors, whether it is sensors based on using the electrical signal or optical signal. These are some of the standard. Of course, the definition changes, but these are some of the performance matrices which people utilized for identifying the uh, how good the sensor is. So one such parameter is called sensitivity. So for a small change in, let's say, for a small change in uh, uh, parameter which you are interested to monitor, what is the corresponding change in either the optical signal or the electrical signal. So that means if you change something like if your body temperature, for example, thermometer. So you know that the thermometer that nowadays what we use either is in non-contact mode or the conventional mercury thermometer. It can monitor the human body to one decimal place, like you have 98.6 degree Fahrenheit, or accordingly you can convert into Celsius. What I'm trying to tell you is how much sensitive a device is, that how much change, what is the rise in the, let's say, mercury level with the change in some temperature. This is how you define sensitivity. So if the change is due to external perturbation is less, but the output signal is more, for a less change, the shift in the parameter or the change in the current voltage or frequency or wavelength or intensity is more, then those are systems which are more sensitive. As I mentioned just to you now, that resolution is another aspect. So the thermometer that we use in day-to-day life is like give you a temperature difference of 0.1 degree. But is it possible that you get 10 to the power minus 4, 10 to the power 5 minus 5 degree change in temperature? Is it possible to come up with a system which can detect 10 to the power minus 3, 10 to the power 4 degree change in temperature? So that decides the resolution. That means what is the smallest measurement? You can not really say least count, but you can say that what is the two readings which can be resolved. So those are called the resolution. Then there is something called as the accuracy of a sensors. And now please note, what we are discussing about is sensor in general, where it can be both. It can be classical sensors or it can be quantum sensors. So this performance matrices for the sensors is general we are talking about. So what is the accurate? So accurate means, can you measure the temperature, let's say to 98.63245? Let's say how many decimal place you can accurately measure. What is the change, to which decimal place the change is happening? This is how the accuracy of the sensors come into play. One of the most important aspect of sensor is the repeatability. That means every time when you do the measurement, the output should be, the calibrated output should be same. And this is very important parameter for a robustness of a sensor. Another thing is a dynamic range, or a range over which your sensor can work. Please note the thermometer, for example, what we have been taking the example, you see that it's varies something around, it will vary something around 96 degrees centigrade to 104, 105 degree Fahrenheit. So what I'm trying to say, that it cannot measure beyond 104, 105 degree Fahrenheit. It can, that's the upper limit of those thermometer. But if you have to measure temperature beyond that, then of course you have to work with some other systems. So the range over which the temperature can work is called as a dynamic range of the sensor. Then linearity, the sensor should be, the devices that comes in the market are largely those sensors which are linear. That means there is a uniform change that happens in the parameter of your interest with the change or environmental change. So it should be linear, but if there are sensors which are having non-linear response, of course one can compensate those non-linear response and still use it. But the good sensors, or the good sensors what exist, most of the sensors that exist in market are having linear, have a linear variation. Response time, as the name itself suggests, that how fast it can detect. So please recall, if you again take the example of a thermometer, the mercury thermometer, you will generally see that you put it, and then there is some display that comes after a beep, and it takes let's say around a few seconds, very few tenths of second, like 30 seconds or 1 minute, maybe 60 seconds. But on the other hand, if you take an infrared sensor, you just sign on the face and immediately it gives you the temperature. So that's the response time. So that means the response time of infrared sensors, which you just signed, those are non-contact temperature sensors, which largely came again for a lot of use during the corona time, because it without touching the patient, you can still use it. So those are basically having a lesser response time. Another very, very important parameter, largely for the electrical systems, is the signal to noise ratio, which are also largely called as SNR. That whatever the sensors once developed, there is always some noise. So those noise, as you know, nobody likes noise. Like even if you, as a faculty, as a teacher, if you go to a class, you don't like a noisy class. So you want a student to concentrate. So those concentration, what is called as a signal. The noise is something where student make nuisance. They don't concentrate on the class. So signal, you always want that signal should be more than the noise. So this is where signal to noise ratio become very important. Drift or stability of a sensors is something which are, again, largely these are dictated by the instrument that what you use. So if you are using some optical instruments, then, or interferometric based systems, largely, then there will be some drift, which are natural drift because of the thermal fluctuations associated with the process itself. Nowadays, everybody is talking about how efficient is the system. When you go to buy a fridge, it's give you 2-star, 3-star, 4-star, 5-star, or even for that matter, air conditioning. So power is a big issue. Energy efficient systems are something which people are interested to make. So these largely are the different performance matrices of a sensor. And the diagram what I am showing you is a diagram related to what are called as a quantum sensors, where you can see that these are diamonds, and then there are certain features associated with these diamonds which are called as defects in the diamond, and those are utilized for making a very, very precise thermometers or magnetometers. These can be much more precise than the conventional thermometer or magnetometer that we use, which are based on classical concept, unlike these NV center defects in NV centers, which are based on quantum concepts. So these are some of the performance matrices of a sensor. So let's go to the two regime of sensors. One is classical sensors, another is quantum sensors. You see this diagram carefully. So if we have some sort of a hill, just imagine, and if somebody can climb that hill, and if the person wants to take the ball, he can't take the ball. I mean, he can't push the ball from this side to this side, passing through the hill itself, for example. So he has to take the ball, go up, and then the ball will come down this side. So this is what is called as a classical physics or classical picture, where you can calculate. Newtonian mechanics allows you to calculate the position of the ball here, the energy associated with the ball here. So this, whatever the energy you have here, it gets converted into the potential energy. Again, it slides down, gets into the kinetic energy, finally again into having some potential energy. So the point what I'm trying to tell you is these domains are classical physics, but in quantum physics, you can have the ball here and it can tunnel through these hills. You can you can think of this hill as some potential, and there's a possibility that this ball can just tunnel out through the hill. It need not to go there. That means ball can also exist here, ball can also exist here, and this is where the quantum picture come into play. If you see the size wise, so particle which largely exhibit these numbers. I mean, when we are talking about 10 to the power minus 9, so we are saying far larger than these numbers. So then you can think it like these are classical particle or big size particle, like you have just 10 to the power 9 minus 9, because we know that typically 1 angstrom we considers for atom size and stuff. But if you are of order of this size, if you are of order of this size where you're just thinking about one atom, then you are in quantum domain. As you can see that these are continuous. These are continuous. Slope is continuous, but here the slopes, you can see these are steps. So you can think something like that classical physics do not discretize the energy level. However, the quantum physics does discretize the energy level. And this is the major difference between the classical physics and quantum physics when you talk about the energy associated with them. So if you see the classical sensors, these are some of the sensors. Electrical sensors can be there, chemical, thermal, and all of you may have seen these sensors at some point of time somewhere in your day-to-day life. But if I ask you that, have you seen these sensors, and the answer is straight away no. So atomic clock, you may not have seen. Quantum classical gyroscope, DRDO in our country at Hyderabad, they make this gyroscope, which are fiber optics based gyroscope, but not the quantum gyroscope still. I have been talking to you about the thermometer, but I mentioned that you can have NV centers or defect in a diamond, and those can be utilized for the development of a quantum thermometer. And of course, imaging is something where quantum imaging, people have started talking about quantum imaging now, where many type of these such type of sensors, quantum sensors can be developed for imaging. Let's first talk more about classical sensors. So all of us know, as I just discussed with you some time back, that if you talk about classical sensors, it will get governed by all these laws, what we are aware about, right? So we know Ohm's law be equal to IR, we know optics, angle of incidence is to be equal to angle of reflection, the ratio between the two, for example, sin I by sin R should be constant. So it gives you a refractive index of a medium. And the observable parameter, as I have been telling you, that you can measure voltage, current, resistance, displacement, etc. That depends that how you want your device to work. So these are some of the classical effect. Many of you must be aware about, whether we are talking about photoelectric effect or we are talking about Faraday electromagnetic induction. So you can just see that you pass this through this coil, and then you will see that there is some deflection. So those movement are basically some change in magnetic flux is happening around, which leads to some deflection in the current. Thermoelectric effect, you require some heat source and heat sink, and then if you correctly join them correctly, you can make these electron flow from source to sink, and you can measure them through some sort of a current. Photoelectric effect are, as I discussed with you, these are piezo. It is not photo. These are photoelectric effect. So, you can create electric field by inducing some electric field. You can measure the electric field by inducing some type of a stress in the systems. Photoelectric effect, for which the great Albert Einstein got the Nobel Award in 1905, that incident some suitable light and you can get some, some suitable light has to be. It cannot be that you go on increasing the intensity of a light, you will get more photocurrent. No, this is where the, major concepts get introduced in terms of H, or the Planck's constant, where H nu, we know that H nu will be half mv square plus H nu 0. So intensity was not the case. It is the energy, or the minimum threshold energy of frequency is required for the photoelectron to get emitted. Then as you do, stretching and pulling of the systems, you see that it gets, due to some mechanical deformation, you will see that some sort of a stress and a strain get created in the systems. So all these can be utilized to measure the Young modulus, for example, of this material. Chemical interactions, all these, what I'm trying to tell you is either measuring voltage, current, resistance, displacement, and so on and so forth. So what are the different types of classical sensors? These are either, it can be electronic, which most of us are aware about. Many of you must be wearing a smartwatch, which is some sort of electronic sensor. So electronic device, it tells you the different parameter associated with the human body. So you can have electronics based sensors for pressure monitoring, temperature. For that matter, all the different type of parameter can be monitored using these electronic sensors, as we have discussed earlier. Similarly, these can be utilized for, all these can be utilized for a lot of applications, whether it is environmental monitoring, biosensing, agriculture. And what I'm trying to tell you is that you can have either electronic, or you can make electrochemical. So the difference between electronic and electrochemical is electrochemical will have some amount of chemical stuff in it, which get dictated by, let's say, some amount of chemical ingredients, unlike the electronic sensors, which are largely dictated either by the flow of current, or flow of current, or you can largely say you measure current and voltage. But here you can also measure some chemical parameters, or you can measure some electrical parameters induced by the chemical change. This is in the market. These things are not yet much more. There are few systems which are in the market, and then there can be a third one, which are optical, which are not coming much, which are not that much great into the market. But I strongly believe that this is a strong future, where in future you will have a lot of optical sensors flooding the market for different applications in physical, chemical, and biological systems. So as we discussed with you, that the market size for the pressure systems is very, very high. And one of the most important area where these pressure sensors are utilized is in oil and gas industry, or where industrial process control need to be there, that how much, at what pressure the systems has to work, or for example in aerospace application, or underwater, you want us to measure the underwater systems. Marine systems for underwater applications are utilized, where a lot of pressure sensors are required. Then you have another systems which are called magnetic. You know that these people utilize for navigation. Sailors utilize for navigation. And nowadays, these magnetic systems are, one of the standards. One of a standard what we have been using is in our day-to-day life is MRI, which many people have to go through when they are not well. So these are, again, magnetic is one area where people are trying to develop. And please note that these are the sensors which are also being now developed using quantum systems, because these are one which has a lot of applications, and therefore people are targeting some of these sensors. Imaging is something, a lot of thermal imaging based sensors are utilized for fire detection or medical applications. So what I'm trying to tell you is that these are some of the types of classical sensors, and they have a lot of potential applications which are being governed. So when you see the advantage of classical sensors and what are the disadvantage it is having, then it is balanced. So but the most important advantage of classical sensors are these are mature technology. People are using for hundreds of years. And therefore, since these are mature technology, it is available either in village, remote part of the village, and it is also available in big cities. Since these technology are mature, things are much more optimized. Therefore, they have some they are good on economics, so they can be cost effective. And since a lot of research has gone in, so therefore we have understood the working principle and operation of those devices. Being classical in nature, you can make them very robust in terms of you don't require systems to operate under very stringent condition. It can work in rugged systems, in rugged environment, and still it can work. Since it can work in rugged environment, they require low maintenance, and they are highly compatible with whatever the industrial standard we have. But these are the good part. The bad part is all these are in red here, this red box. They have limited sensitivity. That means if you want to make a very sensitive device, people are talking about quantum MRI nowadays. So if it has to go, then it will further able to tell you very precise information about an individual human health, which the conventional MRI cannot give you right now. Since it has limited sensitivity, accuracy is not that great with the classical sensors. One of the another important aspect of classical sensors are largely the electronic sensors. It has lot of these signals, a lot of noisy. So all the measurement of the voltage and current, they add to a lot of noise, which are inherent properties of the electrons, which is utilized for the development of these type of electronic sensors. These sensors are big in size, so if you have to operate them, you have to carry from one place to another. It is not easy to carry them at a time. It is not like that you can keep in pocket and you can move around, especially we are talking about the industrial systems. They require a lot of energy. So energy, these people are always trying to do energy efficient systems, but they do require, because system is big, and it requires a lot of energy to operate. And these systems also degrade over time because they are working in rugged environment and stuff. So it is expected that they will degrade over time. So these are some of the disadvantages of and the advantages of classical systems and the quantum systems. Now, can we issue some of these advantages is very good, but can we issue some of these disadvantages what are available with the let's say classical systems by developing some quantum sensors? This is what we're going to see. So let's go to the next part, which is the quantum based systems or quantum sensors. And as I told you that these quantum sensors, in order to go in the quantum regime, you have to operate around these. You have to be at atomic level or size of the atom or subatomic level. And at atomic and subatomic level, what in classical look like just slope, in quantum the same slope look like some steps. And therefore these steps are the one of the unique features of quantum systems, which people utilized for making very, very precise device. So let's look a bit more into this. What are the different quantum systems and what are the different quantum technology? So how these, unlike the classical sensors, which get governed by simple Ohm's law, or let's say simple Snell's law, or law like Faraday's law, the quantum systems work slightly different. And these get governed by a concept in physics called as a subject in physics called as a quantum mechanics. And one of a very important aspect of quantum mechanics is superposition. Now, superposition, if you see, there's a difference between addition and superposition. So when you say that when you add in superposition also, it's you do add, but then the superpositions are associated with they are associated with vector quantity, unlike addition, which are associated with a scalar quantity. So quantum systems has the beauty, when I say quantum systems, that means you are talking about any size of order of 10 to the power minus 9 or energy level, which are having discrete set, not a continuous set. So like, you can talk about quantum systems like atoms or electrons, whose all sizes are for order of that or lower than -9 meter. So these quantum systems, they can exist in multiple states at the same time, unless it is measured. And this is the beauty of quantum systems. So superposition is one thing, which also decides how the system will going to work like. Apart from this superposition, the quantum systems or quantum technology, in quantum technology, things are also entangled. Entangled means if you have seen Hindi movie like Jurva, it is like two identical guy. If you disturb one, the other will feel the presence of. So if a villain hit one guy, the Jurva or the twins will also feel that type of hit. So this is something very similar here. It is called as entanglement here, where two or more quantum particles become linked such that their state are correlated no matter how far they are apart. This Einstein defined this as a spooky action at a distance, and there were a lot of debate about that during that time, and there were a lot of discussions in the scientific community about that time. So entanglement is something like two systems which are entangled, their properties are entangled. So if you disturb one, other will accordingly get changed. So these are called as a quantum entanglement. Quantum tunneling is something which you can just you can imagine that as I told you, that if you consider some hill, and if you if the size of that hill, can be if the width of that hill can be thought of the size of an atom, like of order of 10 to the power 9 minus 9, that size, then it is possible that the particle again of that size, 10 to the power minus 9 or below, can pass from without really crossing the barrier. It can just tunnel out from one through those barrier, and it can be measured on the other side of the barrier also, which are not possible with classical systems. And the most important aspect of quantum measurement, that measuring a quantum system collapse it in this, you must understand. Measuring a quantum system collapse it into one of its possible state, giving unique way to extracting an information process. This is what was made, way back. It was made way back when quantum mechanics was getting developed in the last century, that as soon as you try to measure it, it collapse. So that's the beauty. So that's the beauty and also the beast of any quantum measurement. But then there are ways, the collapse nature of, if you measure them, it collapse. So people try to study those collapse and try to decipher information from them. So these, unlike the classical systems which uses Ohm's law and Snell's law, the quantum phenomena uses these principles like superposition, entanglement, tunneling, as we discussed. Another is squeezing. So let's not go much into those. These are some of the advanced stuff, but you can think that these are also based on the concept of quantum phenomena. What it measures beyond classical physics, like what classical limits cannot do, quantum systems can do. So I have just tried to show you some of those concepts of quantum superposition, entanglement, squeeze state of light. Now these are the quantum phenomena which are utilized for the development of quantum sensors. So if you see superposition, so if I ask you that whether this guy which is moving around here and there is at 0 or 1, it will be difficult for you to predict whether it is. So now you can see at 1, now you can see at it is at 0 and it goes to 1, but in between, if you see that it is as both, it can be, there's a finite possibility of being at 0 state, there's a finite possibility of being at, let's say, 1. So these are some sort of a superposition. You can say that it is some finite, you can measure the probability, finite probability is associated with being at this location or at being at this location. As we talked about quantum entanglement, you can see that these are two particle systems which are talking to one another, even if they are separated. When they comes closer or they go far apart, still they are interacting with one another. So these are called as quantum entanglement. Squeeze state of light, it has attracted a lot of, it also the concept of short pulse amplification got Nobel Award also. So this squeeze sort of light, where you can see that you are choosing this light in order to create some single photon. People create such type of single photon using these squeeze state of light. Yeah. People who talks about quantum computer, and it's a lot of measurement associated with quantum computers or quantum systems. They basically uses one of the way they use is also the spin state or the coherence associated with that. That means they try to measure the spin up or spin down, and then it's in the superposed state, which are utilized for development of quantum sensors. Quantum tunneling, this is something like that. You say that you see that it's written, you shall not pass. This is what it is there. So this is electron. You have no power here, but it can also come this side. It can also come this side. So that depends upon what is the width of this tunnel. Unlike classical interferometry, like all of us know about YDSE, young double slit experiment, quantum interferometry utilizes the single photon. So this is a setup which you can think that this is some sort of, you say one photon is going on, it goes to the two part, and then it follows there, and there is a beam splitter. So you have some photon going this side, some photon going this side. So you do the correlation of these two photon, and then try to develop what are called as a HBT or Henry Bros and Bound and Twice experiment, which are classical, which is one of a quantum interferometer which are utilized for quantum sensing and metrological application. So all of us are aware about GPS. These are atomic clock. So these are already in utilized. So people are using this. This is one of example, you can say, of a quantum systems which are already in place. These global positioning systems are largely based on this atomic clock, which utilizes the concept of quantum physics. And it has a lot of applications, needless to say, about in telecommunication, astronomy, radio telescope, defense, military, and satellite and earth communication. This is what I was talking about, that people are talking about quantum magnetometer, which can be utilized in NMR or MRI, or it can be utilized to detect different type of mineral exploration, which are otherwise not possible with quantum systems, and for different detection of underwater submarines and stuff. This is another very hot area of research. What people are using are called quantum gravimeter. These are utilized for monitoring the different type of volcanoes, eruptions, seismic studies, and climate change. So these again are very. We have some very good group in India working in this, and we have some speakers who will be talking about this. I hope he will touch upon some of these quantum gravimeters or the concept utilized for these development. So as I was talking to you about quantum gyroscope, unlike classical gyroscope, uh, it can be utilized for submarine navigation, military applications, explorations of marine and aviation safety. These are something which are, again, a lot of applications for defense application. Quantum imaging, unlike classical imaging, these are expected to give you, also these are called as a ghost imaging. These are expected to give you what are called as a super resolution microscopy. That means you can, please recall that one of the limitations of a classical sensors are lower resolution. So these quantum sensors are expected to give you much higher resolution, which can be possible with this, imaging, which which are possible with these quantum systems that can be utilized for either hyperspectral imaging or super resolution microscopy. Again, quantum thermometer, where you can utilize them, it can be utilized. Please note, in future, when the drugs will get customized, you need to monitor those small, drugs at atomic level. You need to monitor how much the temperature change happens when let's say, when it interacts with the nearby environment, either in human body or outside. So for those, very precise thermometry will be required, which can detect temperature of order of few 10 to the power minus 4, 10 to the power minus 5 degree change in temperature. So such type of systems measurement, or beyond that, not only minus 4, minus 5, beyond that. So such type of measurement is not possible with the classical thermometer. So you need to have quantum thermometer. This diagram largely shows that, please note this word precision measurement. This is what Feynman has written in his book, that majority of the physics related, the fundamental physics related work has been largely covered in the last decade. So we have unwinded a lot of new physics, but this century, the current century, what we are in currently, will be utilizing those physics to do what are called as a precision measurement. This is will be the future. How precisely you can detect, how precisely you can monitor will going to be the future. So for in quantum, so people are talking about quantum internet. What we are using is a classical internet. So you have either you measure 0 or 1, but in quantum, when quantum communications will going to take place, you're going to see that it is some superposition of 0 or 1. It will the system will not measure 0 or 1. It will measure some amount of 0, I mean layman's term, some amount of 0 and some amount of 1, so in some superposed state. Then of course I discussed about quantum entanglement. Then you have what are called as a quantum key distribution. This is also called as a QKD. So these are now some of these QKD are based on random number generations. In our country also something has been developed for this, which are called as a QRNG, quantum random number generator, where you can see that you create these 0 and 1 randomly. So and what it does, it simply uses some light source and a beam splitter. So whether the photon will pass through this or it will pass through this, you don't know. So it is just randomly can pass through one arm at one time and another arm at another time, and you generate. When it pass, you say 1, or if it get blocked, you say 0. So this is one way in which QRNG people are trying to generate the random number. People are talking about quantum teleportation. Please note, Einstein gave the concept of E equal to mc squared, that mass can be converted into energy and vice versa. Some advanced form of that is what people are talking about. Can you go in past and present? Can you move to in past and stuff? So these are all too in a too early stage. There are a lot of research is going on quantum computer. There's a race. You already know that IBM has developed a quantum computer, and then there's a race to develop some sort of quantum computer worth 1000 qubit systems and stuff, which will able to solve a lot of problems which are existing, but then it will open a worldwide, it will open a race to develop such type of systems, because then breaking all these passwords, 128-bit encrypted systems and stuff, it will take few minutes to do that, or few seconds for that matter to do that. So therefore, a lot of research people are trying to do in quantum computing related based, quantum sensors. So if you see quantum sensors, what are the advantages of these quantum sensors? So whatever the disadvantages of classical sensors were there, those can be overcome. So you can make very ultra high sensitivity. You can have very, very precise system. How precise are precise? So we are talking about development of 10 raised to power minus 15 Tesla of magnetic field. That means femtotesla magnetic field are possible using these quantum systems, where you use rubidium based atomic systems, or you used NV centers based systems which are defect in diamond. You can have a very good imaging leading to some hyperspectral imaging, or super resolution. Now all these quantum systems will have very less noise, because these will be they will not get perturbed by the environmental noise. So this is what is expected. For many of the biological application, you don't have to be invasive. You don't have to prick the human to get blood and do the analysis for test and stuff. So it is expected that non-invasive sensing will be much more easier using quantum systems, and these are very, very small. When you say so, you may correct me. It is not correct me. You may confront me, saying that current quantum computer are very big. When I am saying it is very, very small, I am talking about the systems that are utilized to develop these are small. Of course, the whole optical table or the whole systems is as big as a room size now. But in future, as things will grow, these are expected to have a potential of making it small. So the measurement, what we are trying to do is on a very localized, local scale, but although to detect them, you require a lot of other things associated with it. Now, these are big disadvantage, and therefore whole world is trying to put money because they are very costly measurement. So to develop a good, government of India has already kind enough to give a lot of money for this national quantum mission, where the idea is to develop these quantum systems. So these are very expensive systems. So one need to put a lot of money, a lot of research need to go. Operations are, as I told you, that you don't have a zero and you have some superposition of zero and one. So their working is not that easy. It's a complex. They can be temperature sensitive depending upon which device you are talking about. Not that all systems will be temperature sensitive, but some systems will be temperature sensitive. Uh, uh, there are already race to develop systems, but whether it will be commercial available in future, how long it will take. But currently, it is not that much available. So limited availability of quantum, for example, quantum computer is there. Uh, Integrating them with the way classical systems are integrated with day-to-day activity will going to be another big job which are at the hand. Uh, then these will going to take time. It is not coming very soon, so it will take time for the development. So let's try to quickly see what are the different classical and quantum sensors. Aspect-wise: sensitivity, precision, calibration, cost, complexity, and maturity. If I have to summarize in this, so these are extremely sensitive. They are very precise. As I told, here it is, you have classical noise, but they can get using quantum effect like quantum confinement and stuff. They can really surpass some of the precision. Uh, they get perturbed by lot of drift, but they are have little drift, or they are more going to be more robust once it is completely developed. uh, as of now, these systems are not scalable. You cannot quickly go to 1,000 or 1 lakh of qubit. People are struggling in our country. We are still not even in 2-digit based qubit system. These are very complex. You require a special type of labs infrastructure to develop that, and it requires a lot of, lot of iterations before it can be really coming into for day-to-day activity, or it can be utilized as a commercial systems. Then where these can be utilized, these are classical sensors where you use for automotive industry, but these can be utilized all the metrological institute. So you see many of these are available, but that precision at which you can do the measurement are not possible with this. Not possible with this. These are already many places being utilized, but then the limitations of this can become with quantum based systems. So if I have to tell you that how these futures look like, in classicals, we are aware about this MEMS and NEMS based small sensors, which are integrated with many devices. People have also used Internet of Things for real-time monitoring. Healthcare in classical, people are talking about flexible and wearable sensors. Imaging, AI, people are using to enhance the sensing. So these are some of the classical systems, but if at all the quantum systems get completely developed, it will be utilized for field deployment. So these will be very going to compact. You can directly, unlike IoT, you can directly integrate. I was talking about quantum internet. You can directly integrate with quantum communication network. Healthcare, will be much more customized in future. So if you have quantum based sensors, so you can really do the diagnosis of individual at cellular level. So this will going to be what very, very fascinating research, where people life expectancy is expected to rise further because the healthcare will get further much more advanced. These are requires time, as I mentioned to you. It's not scalable as of now. So there are advantages and disadvantages of quantum systems, and whatever the classical sensors, what we are using those into keeping those into consideration where maximum amount of sensors are being utilized, one can plan to build the quantum sensors in future. So I try to give you some brief overview about classical and quantum sensors. We use it in day-to-day life. These are scalable. They are very mature technology. But quantum systems are not mature, but it is expected to deliver beyond these classical systems. Uh, we have all seen already. We have seen AI, IoT, miniaturization. All are in, classical. People will going to use them more in future, but future quantum will be largely used for humankind, which is changing the everything. Let's, for example, there will be paradigm shift in healthcare applications, defense, and so on. So these will going to have a huge impact over human being if in future quantum sensors are developed. So it will going to change the way things are being measured. uh, it will overcome many of the limitations of what the existing systems. So both will going to exist even in future. It is not that classical sensors will go away, only quantum will take. As I told you, there are a lot of challenges. It's very expensive. Scalability is issue. Both will exist, but then as a human, will be taking the best of both the world to see how things can, be utilized to solve the problem of humankind. So with this, I would again acknowledge everybody who is involved with this, my lab, and also I would like to thank all of you for your kind patience and listening. Thank you very much.
Thank you, sir, for your this wonderful. Again, request participants, if you have any question or queries, please feel free to write in the chat box so that we can read and the speaker can respond. I'm not able to see any queries till now in the chat box. If you have any queries, please feel free to. Okay. Sir, can you please check this message?
Pardon?
Can you check the message? Because
Okay, okay,
participant has some queries.
okay. Let me see. It is Professor Y. Maruti. Since classical sensors dominate wearable healthcare and quantum sensors focus on molecular level diagnostic, what would be the realistic pathway for quantum sensors to enter the wearable market? So as I mentioned to you that classical systems are something which we are already utilizing. So making these quantum sensors to market will take time, but once it comes to the market, it will going to do wonders. So let's say the classical healthcare band, wristband, what we are using today is giving a generic feature. I mean, it is not really, anybody can wear it. It will tell you some average oxygen content in the blood, heart rate. It will going to monitor, or for example, it can tell you that how many steps you have taken. But once these quantum systems get developed, or quantum sense wearable quantum integration can be done with the wearable systems, it will tell you why such things are happening in your, why such thing that in the evening you are having blood pressure, let's say, which is higher than the morning, uh, because of which particular parameter it has gone down, whether it is because you have taken some other uh, food which is rising it, or you have worked out more, or you are more tired. So those finer details will going to get integrated in future, and this is where the quantum systems will make changes. It will be more customized from individual point of view. But to reach there, I think a lot of research need to go. Usage of quantum system sensors. I hope I am clear to Professor Maruti. Then Dr. N. Ravi. Usage of quantum systems in medical surgery is remote. How it is advantage over IoT. So quantum systems again in medical, as I told you, that once it is developed, because we're going to take advantage from the existing classical systems to utilize for remote surgery. So, but development of such quantum sensors for surgical applications. So, what you are talking about, please note, for surgery and stuff, you more require more of a classical systems, like, but to do the precision surgery at cellular level, you need to come up with such type of scissors and tweezers which can operate at that scale. So once you develop that, then of course you can do the remote surgery, integrating the quantum technology, but the help need to be taken from whatever existing in the classical domain. So this is Dr. N. Ravi. Professor, thank you. One more question, please. You mentioned miniaturization potential as an advantage, but also integration challenge as it is. Where exactly does the bottleneck lie for wearable applications? Miniaturization as an advantage, but also integration. It's what I can make out from your question is, if you're talking about integrating quantum sensors to wearable systems, the largely challenges lies in the current way, the current way in which you require the type of sources. For example, we are talking about, when we're talking about wearable systems, so the type of sources which are required, that the type of sources which are required to excite those quantum phenomena, like for example the transition that takes place to give you the fluorescence in NV centers from MS, let's say MS plus minus 1 to MS equal to 0, the spin transition that takes place, the type of sources that are required is all big. You cannot get them for the variable part. So if you have to make them to the variable part, the first thing you have to really miniaturize some, you have to make some sources which are of that scale, like very small sources which can be integrated with the device. Similarly, the detectors that are there need to also further miniaturize. So once these things, the sources and detector can be miniaturized, then only we will able to integrate to the variable systems. LLM tuning to quantum sensors, is it in process? What is LLM tuning? Sorry, Dr. N. Ravi, what is this LLM tuning to quantum sensors? Is it in process? What is LLM? AI application. Sorry, I'm not aware about this. Large language modeling, maybe, sir. No, I'm not aware about. Look, people are using AI, but AI in quantum, you can see some papers are started coming up, because this new area, people are trying to do something and get published. But it's too early to really comment how these will be utilized to integrate, because AI works on the available information, data what are available. But currently there are not many data available for the quantum measurement. As I told you, these are very expensive experiments. So one need to do more experiments where AI can use AI can be trained with those data to give you some good predictions for future. Okay,
So thank you, sir. Thank you,
Raja.
sir. So I could see there is no more questions.
Yes.
So on behalf of participants as well as our on personal behalf, I thank you for your wonderful lecture and time. And we look forward for few more sessions in this FDP. So once again, thank you for your time and joining for today for this lecture.
Thank you, Professor Avasti. Thank you very much for this opportunity. Thank you.
Thank you, sir.
Thank you.
Bye.
Bye.